Hello and welcome to today's webinar, Optimizing Power Supply Design. My name is Sarah and I will be your moderator for today. Before we get started, I'd like to address a few logistics and details on the GoToWebinar platform. If you are unable to hear the presenter or see the presentation at any time throughout the webinar, please let us know in the chat and we will do our best to resolve any issues. If you have any questions throughout the webinar, please type them in the question panel as they come up. We will have representatives ready to answer your questions directly during the webinar. This webinar will be recorded and posted on the EMA resource page. Once this is posted, we will send everyone who is registered for today's webinar an email with a link to the recording in the next couple of days. That being said, I want to thank you all for joining us today and introduce you to our presenter, Roger Chen. He's a Colorado-based field applications engineer who has been with EMA Design Automation since 2013. He focuses on component library management, design data management, and SPICE circuit simulation. Roger will start off the webinar explaining what power supply design is, following by a demonstration. Assuming we have time at the end, we will field some questions in a formal Q&A. Thank you for your attention, and now over to you, Roger.
Thank you, Sarah, for moderating. So, thank you everybody for attending our webinar today. My name is Roger again, and our focus today will be on building and designing better power supplies and the techniques we can use to identify problems we have early on so that we don't run into issues when we actually put it onto a breadboard. So let's get started. What is power supply design? We want to be able to ensure that we can convert a potentially variable input voltage into a fixed output voltage. And one of my main goals today is to show you how simulating your power supply design before you even build it in a prototype can really help you identify core issues early on. So we're going to do in our flow today, we're going to start with a very ideal converter just to see that we meet the desired input and output criteria. And then we're going to add on some of the effects of our switching controller and then the effects of our parasitics on our converter, and then talk about how we can optimize that component selection process. Now that we're aware of our parasitics, we want to see how our input and output capacitors and inductors are affected by tolerances or changes in our build. So once we've done that, we can check for the power dissipation using our root mean squared measurements of our currents in our design, and then use that to find out the amount of heat our power supply would generate. Consider the larger effects of the issues we run into with power supply design. When you have issues that you find after you've already built your prototype, you'll have reduced yields. You might have reliability once you have your production board in the field. You might have to respin your boards. You might have to buy components and swap them out in later production cycles. And all of this can cause delays that will cause you to miss your time to market schedule. So we're really hoping that the simulation techniques we show you today will help address some of these issues and find design issues before you even reach any of these potential quagmires. So let's start with a very simple and very common buck converter where we can take an input voltage, use a switching controller, and step down the output voltage depending on that D duty cycle we are operating under. One key thing to note is your average output current on your load there is going to be the same as your average inductor current for this topology. So with power supply analysis at a very simple level, when you have the controller turning on the MOSFET there, your voltage across the inductor will be the difference between the input and output voltage. And then when the diode is on and the MOSFET is off, your voltage across your inductor would just be the negative polarity value of the output voltage. So we can take this simple ideal converter and build it in a SPICE simulation. We just want to confirm that we pick an ideal inductor, an ideal capacitor, and we can put in a 25 volt input and generate a 12.5 volt output, which we can see there from the result of our SPICE simulation. Now we're starting at a very ideal level just to confirm the components we picked there. But let's start capturing more of the real world effects. So we want to be able to find a controller model that can capture some of our more real world features. You have your pulse generation, you have your amplifier that is tied to your feedback loop, you have your soft start function, which we can model with switch inside our SPICE circuit. You'll have input protection on your voltage, meaning that you don't want your power supply controller to be sending out voltage pulses when the voltage is too high or too low. And likewise, when the output current is too high, we want to be able to shut off our voltage supply as well, so we don't overheat our board. Now, ideally, you'd be able to find what we call a sub-circuit model that a manufacturer might give you that is an average switch model or a state average model, as they're called. If you can find one of those, that's really good news, because that kind of sub-circuit model can be used for not just transient analysis, which is what we're going to mostly focus on today, but also for AC simulation and loop analysis. So without diving too much into the math, you can see on the bottom here what a switch network or average switch model does for you is it separates the time invariant components from the time variant components, meaning the inductors and the capacitors. So then you can essentially treat your switching network as a large signal, nonlinear, and time invariant model. So you can do things with it that you might not be able to do with the transient models you get and some of the techniques we show you today. So if you can find that, that's great news. Plug that right into your circuit and try to simulate with it. If you can't find it, we're going to offer you some techniques here today that can replicate some of those features. So with our pulse width modulation controller, the pulse we output is of utmost importance. And we're going to model that with a ramp sawtooth voltage source. And then we're going to use a switch with some on-off resistances, some threshold and hysteresis voltages to mimic a comparator block for our feedback loop. You can notice there on the bottom right, you can add in some delay as well if you want to that switch. Most switching controllers will have input voltage protection, meaning you're going to want to build on your circuit some way to reflect the controller's ability to turn off when the input voltage is too high or too low. In this case, on our bottom left, we have protection against, we're using that switching model to protect against our input voltage from going below 20.5 volts. On the right, we're protecting it from going over 29.25 volts. The 0.25 is that hysteresis voltage. With the soft start function, we can use a voltage controlled switch tied to a capacitor so that you can see here we'll gradually ramp up our output voltage instead of having a huge spike and way overshooting our desired output voltage goal before settling to that desired level. So make sure you are able to replicate that effect so that you not only get an accurate behavior, but you don't cause convergence issues with those huge voltage jumps. Likewise, the current limiter is very important on your switching controller. And we can use essentially a gain block here to take that current and measure it as a voltage and then tie it to a behavioral block, we call it in SPICE, so that we can say if our current here exceeds 2.5 amps, then let's cut off our voltage supply. And you can see here on the left on that plot, we purposely put in a spike so that we at 1.75 or 1.8 milliseconds, we jump up to about 3 amps and we can see our output voltage cuts out to compensate for that. So having modeled some of the controller effects, or if you're able to find a nice average switch model for your subcircuit controller, now you can focus on tackling your input and output ripple. And the inductor and capacitor components you pick are very important for controlling those factors. But not only the absolute values of those components, but you have to take into account the tolerances. Nowadays, many power supplies fail because the capacitors that are selected for them are not of high quality and have tolerances that can exceed what your desired goals are. So if we set some desired goals like we see here on the right, we can use a Monte Carlo technique perhaps to predict how variations in that tolerance range will affect our yield. How many percent of 1,000 boards we build will fail. Likewise, we can use, as we build more complex topologies in our power supplies, it's harder and harder to figure out what exact components have the biggest impact on our output goals. So if you first define your goals, there's a lot of SPICE techniques to do some sensitivity analysis, find exactly what component is causing the most impact on our goal. So we can see here on the top left, the junction capacitance on one of our MOSFETs has the most sensitivity detected on one of our goals. And then we can use in the table below, in the image below, we can use what we call our real-world component table, assign a list of capacitor values, resistor values, inductor values that you're willing to use, and you can use our optimizing technique to minimize the difference between your goals and what those components can give you. That way you're driving, and essentially it will do the work of solving for what component values can best fit your circuit. Another reason to build this simulation, so that if you need to make changes in the future and you need to change your goals, you can easily reassign different goals and optimize the different component values. So with those inductors and capacitors, when we simulate them, we have to consider them not only as inductors and capacitors, but take into account their equivalent series of resistance, the ESR that you often read about and you'll see on the data sheets. But you also need to take into account things like the self-resonant frequency of your inductor. So we have some SPICE templates here on the bottom right. You can calculate your self-resonant frequency if you provide the series inductance, the series resistance, and you can see that essentially you're creating a sub-circuit for what your capacitor or inductor is really like on your circuit. As a good design tip here, be aware that some capacitors, especially your ceramic capacitors, will lose capacitance as the DC bias increase. And you can model this effect in SPICE as well by putting in a voltage controlled capacitor so that you're seeing exactly, if I use a capacitor with 25 volt rating and I'm approaching 15 volts with DC bias on that capacitor, what is my actual capacitance and how does that affect my output from my converter? And from personal experience with many customers, I've found that they've been using power MOSFET models that don't capture the source and drain areas. If you don't have those areas defined, you're not going to capture the junction capacitance or overlap capacitance on those transistors. With your power supply design, having good magnetics is a huge factor in your having a good output, and also in the ability to handle any variations in your input or in your load. So when you do a SPICE simulation, don't just consider the ideal inductor or transformer. Make sure you put in the shape and the core type, whether it be a ferrite core or a powder iron. If there's an air gap, you can model those in SPICE so that your simulations reflect the behavior accurately. For example, a flyback converter, we know that it stores the magnetic energy in the inductor air gap. So if you don't model that air gap, you will not have an accurate SPICE result, and you won't be able to meaningfully capture any issues in your power supply design. So we see here on the bottom right, on the top we have an ideal transformer, and then on the bottom we've added in some of the non-ideal effects in our magnetic core, and it drastically changes how our transformer behaves. And with magnetic parts, you should take into account the losses, especially the hysteresis loss, as the core charges from positive to negative, saturation, and back. And we call this a BH curve, and usually you take the integral of the BH curve so that that area inside of it will tell you how much hysteresis loss you have. And the more hysteresis loss, the more heat you'll have on your power supply. So you should use something like this hysteresis loss calculator. Once you reach steady state, you supply the core volume of that magnetic core, and you can calculate using the frequency how much power is dissipated through hysteresis loss. Once you have a pretty realistic representation of your power supply design in your SPICE circuit, you should start putting in tests like input variations. So your input voltage is often considered less important than your output voltage ripple. But in many cases, you'll find that having peak-to-peak noise on what you would normally put as an ideal DC source, or putting a voltage change in your input, can really show you that your power supply design is not as flexible as you think. So here on the bottom right, we have in orange our output voltage. In yellow, we purposely put in a spike for our input voltage, and we can see that for our circuit here, our output voltage is not knocked off. It doesn't suffer from any instability with a voltage input spike of this size. It's able to respond well and readjust to that change in the input voltage. With your output testing, you should test drastic cases like what happens when I have a short circuit in my load. Ideally, your circuit, the switching controller, would stop supplying those voltage pulses if it detects that your load is shorted. So here we put in a little transistor and a voltage source that turns on at 800 microseconds. And we have here the voltage pulses coming out of our controller. And we are able to confirm that in our circuit here at 800 microseconds, it cuts off those pulses. And then when the short ends in our load, we have our soft start where we're trying to ramp up our output voltage, and we have more dense pulses before it reaches steady state and we return to our previous duty cycle. As you play with SPICE simulations more and more, you'll find that especially at higher frequencies and with higher current power supply circuits, you'll run into convergence issues. So here I have a flyback converter that I was simulating, and even though I'm using a linear transformer, meaning an ideal transformer there, I was still suffering from convergence issues. What I did was I measured the currents running through some of my components here, and I found that they were much higher than what I normally experience in my other simulations. So as a rule of thumb, you should not have any currents that are on your simulation that are 9 orders of magnitude larger than the SPICE tolerance. So here on the bottom, we see that the absolute tolerance, which is the current tolerance the SPICE simulation engine is using, is at 1.99 microamps. That's what it took for it to simulate with autoconvergence. But the default value was at 1 picoamp, so 1,000 times smaller. So make sure to loosen that absolute tolerance when you're trying to do your SPICE simulation for your power supply circuit. So let's move into the realm of heat now. We've talked a lot about picking the right components, but an underrated factor for power supply failure is overheating your components and overheating your design. Your capacitors, your inductors, your MOSFETs, the controller itself, their behavior might change as your power supply heats up. So if you're going to be using heat sinks, and many of you will, make sure to model the effects of those heat sinks on your simulation. I don't have a bullet point here, but sometimes you need to take into account the parasitic inductance that you can have caused by putting in a heat sink as well. That can potentially be a cause of issue. But in a more ideal world, we're going to specify our derating specification. We're going to tie to each of our components that have a heat sink. And then we're going to run a MOC, a maximum operating condition, or a smoke analysis to detect which of our components suffer the most from the heat in our power supply. And when you think of heat, think of RMS current measurements, meaning root mean squared, which is the most common way and usually one of the best ways to measure power dissipation, and with power dissipation, your heat. So we see on the right, we have a list of our components, their deratings, and some of them use peak-to-peak measurements, other ones use root mean squared, and you can see exactly which ones and by how much their derating is exceeded. And it's nice to do this in the SPICE simulation because in real life it can be a challenge, even with many oscilloscopes, to measure your root mean squared currents accurately. And in the bigger picture, I've found more and more customers using digital power supply techniques. And when you are trying to simulate that in your tool, you need to make sure you're simulating the analog to digital converters so that you can see in the bottom there that the effect of your ADC is not impacting your circuit behavior as well. And for many of my automotive customers out there, I found that they have models for their controllers built in either C, System C, or in MATLAB. And it can be important to see how your SPICE simulation works in conjunction with a controller that's designed in another language. During our demo today, I can show you a little bit of that. But to step back in the big picture, we want to emphasize to you that by simulating your power supply design and capturing those real-world effects of the parasitics, of the controller, of your losses in your transistors, you can tackle real-time changes and issues and proactively streamline your design cycle. Instead of building 4 prototypes, we can build 4 virtual prototypes in our SPICE circuit and test its effects, and then more quickly deliver our product to the market. So I'm going to dive into our OrCAD workspace, which is where we're going to design our schematic, and then it's tied directly into our PSpice simulation tool. So as I mentioned, we're going to start at a pretty ideal level with our buck converter. We don't have a model for a controller, so I just put in a voltage source. You can see the pulse width is 100 microseconds over a period of 200 microseconds, so we have a 50% duty cycle. So we should be able to take this 25 volt input and then generate here on our load a 12.5 volt output. And here things are modeled pretty ideally so far. We're starting at a starting point just to pick out and test our inductor and capacitor values in conjunction with our transistor. So if I run my PSpice simulation, I can see that I have my 25 volt input, and I'll turn my cursor to measure that we are able to get a 12.365 volt output here once we reach steady state. So fairly straightforward, but a nice verification for the inductor values and capacitor values that we've picked. So let's step into tackling some of the more non-ideal effects. So if you can find an average switch subcircuit model for your controller, that'd be wonderful. If not, let's see some of the techniques I showed you during the slideshow. So here we've taken our converter topology and we've added in some circuitry to mimic and replicate our controller effects. We have our input voltage here. I'm going to use my PSpice modeling template. It's nominally at 24 volts, but I'm going to purposely put in a drop to 19 volts at 1 milliseconds so that we can see the effect of our input voltage protection on this circuit. And let's move down to our input circuit protection. So down here are some of those switches I've mentioned. And if you're familiar with PSpice, and even if you're not, there's some great templates here under the PSpice component modeling app. And you can model transformers, voltage control oscillators, and here a switch. So we can assign our switch. You can make it a voltage control switch like we have here. And our switch will turn off if that input voltage exceeds 21.5 volts there. If it falls below 20.05 volts there. And if it exceeds 29.25 volts here with the over voltage protection. And from our input, we can also check for our soft start, our pulse generation. So we have our ramp source here. Let's take a look at that template. And we're using a ramp sawtooth waveform going from 0 to 3 volts in 2 microseconds. And we have a comparator loop using our air amplifier down here. And we're using our soft start circuitry here with the ramp tied to our capacitor to gradually turn on our voltage output instead of having a huge spike, as I'll show you. So our air amplifier is tied to a voltage divider here. We call this a sense resistor. And then on our output, we can put in a voltage controlled switch tied to a voltage source where we can change our load. So at 1.8 milliseconds, we're going to change our load, and we'll see the effect of that on our simulation. And finally, we have here, we're measuring the current coming out into the load, and we're going to use this gain block to convert the current into a voltage, and then we can simply use this e-value behavioral block and say if our voltage, meaning our measurement of the current there, exceeds 2.5, then cut off our voltage supply, our voltage pulses here. So let's run this simulation. It might take a few seconds to run. But while we do that, I want to talk about the parasitics and modeling the parasitics and some of the PSpice modeling applications that can help you with that. So we've already seen the application for switches, but for your inductor and capacitor, you can capture the series resistance, the series inductance, and then you can calculate it will calculate for you from that the self-resonant frequency of that parasitic element. And again, if you have temperature changes due to your power supply heating up, the temperature coefficients will model the effect of that on your capacitor as well. Likewise, we can do that with the inductor. You can capture the series resistance, that DC resistance as some people call it, if you have a parallel resistance, and then if your switching frequency exceeds the frequency, the self-resonant frequency of this inductor, you can see its capacitive effect as well. So all inside this template. And alrighty, we have our simulation run. As I mentioned, we have our soft start. I've already run the simulation without the soft start, so let me append that data to show you how it looks like. And we can see here, without the soft start, we have a huge overshoot. And by using our soft start effect, we can more accurately reflect that behavior. At 1 millisecond, we had that voltage source here, dropping our input voltage below to 19 volts. And we can see that we cut off our voltage output here because of that input voltage protection. So I've mentioned parasitics, I mentioned techniques to model your controller. Now let's talk a little bit about the magnetics. So if we have our buck converter here, we can take our inductor and we can tie it to this magnetic core part. So here, when we look at the SPICE model, we can see that this is no longer an ideal SPICE model. It has an area, it has an air gap, and we can use that non-ideal model now to capture the effects of the hysteresis loss. So let's run this simulation. And we can see it reaches steady state definitely after 3 milliseconds. If we look at the data sheet, we have an effective volume of 309 cubic millimeters. So let's plug those values into our PSpice hysteresis loss calculator. And we can say from 3 milliseconds to 5 milliseconds there with 309 cubic millimeters for a core volume. It will automatically detect the frequency in our steady state, and we can see our hysteresis loss here is pretty small, 0.97 or 0.0972 watts. So pretty good using that inductor there. Not much heat dissipated because of the magnetic hysteresis loss. If you want to visualize your BH curve, I'm going to add a new plot. And I'm going to insert the B curve. And then I'm going to change my axis setting. Let me remove this plot just to give myself a little more room. Add the B again. And I'm going to change my axis settings. And I can change my my x-axis here to be, instead of time, to plot it against the H curve. And when I do this, I can plot the BH curve here, and we can see it's pretty narrow. If I zoom in, I can use the zoom area command in PSpice. It's very narrow. That's why we have very little hysteresis loss. Inside of this curve, there's not much area as the core charges from negative to positive polarity. So it's a good magnetic core. We can use that part. And then, as I mentioned, you guys will often find that you have show you my MATLAB co-simulation. So with PSpice, we can co-simulate our model or SPICE circuitry that we build with other models. And what I've done here is we've taken a converter topology, build it into SPICE, and we can see, if you guys aren't familiar with the SPICE block here, what you do is you simply assign the voltages that you're going to replace using the MATLAB models, You pick out the voltage, the current, the wattage. You can select any of the nodes or currents, the node voltages or the net currents to pick out as outputs from their SPICE. And you can tie that to your Simulink models. So if you have electromechanical loads you want to model, if you have a PWM controller built in MATLAB, you can tie that now to your SPICE circuit. My project has already been specified. I have a PWM controller that I've built in MATLAB, and I can run this, and this has additional power over PSpice, and that I can change the load, and you can see the change in our output voltage live within our simulation. In PSpice, it's not so easy to do a live change in our loads or change our inputs to our SPICE simulation, but by tying it to our MATLAB Simulink co-simulation, we can now do a live simulation using SPICE circuitry and models in other tools. So for any automotive customers out there, this has been a very popular request from our customers. Alrighty, I'm going to pass it back to Sarah, and if you have any interest in seeing those SPICE templates or getting an application note from us, please reach out and we'll be glad to share those with you.
Okay, now is your opportunity to ask any of your questions. Okay, Roger, our first question is, are there other ways of calming a circuit that is having a hard time of converging?
Yes, so in our PSpice tool, we can use an Autoconvergence tool, and I mentioned this a little bit in our slides, and it's good that we bring it up again. But when you set your options, you can turn on the Autoconvergence-ish option here in PSpice. And what you'll do here is you're specifying how much to loosen your tolerances so that you're able to simulate. And as I mentioned, the absolute tolerance for the current here, that's the one that often causes your power supply circuits to not be able to simulate. If you increase the value or use the auto-converge to specify how much this can increase to, then you'll be able to better find a convergence issue. Also taking into account that you've properly modeled your power transistors so that they have junction capacitance, the drain and gate areas modeled, so that can sometimes cause convergence issues as well. Thank you for that good question.
Okay, the next one is, can PSpice analyze the circuit stability in the frequency domain?
So PSpice does have, before I close out here, PSpice does have a AC analysis tool, but it does take small signal approximations. And as I mentioned, if you're able to find a nice sub-circuit model for your power controller, and there's a power IC package that we saw there of SPICE libraries that include many of those average switch models, then you're much better off in simulating your frequency domain response. But if you're using our transient techniques we showed today with a controller, you can run into convergence issues and you might not get as accurate a result. But there are techniques, and we have application notes we can give you for capturing some of the frequency response and loop stability of your power supply circuit that might be able to help you even if you can't find a very nice sub-circuit model.
Can other types of power topologies be simulated other than buck?
Yes, so I only showed the buck today just for time focus, but you can take most of your common topologies, you can even combine them, get more complex topologies, and you can simulate them in our PSpice tool. And we can capture the effects of the parasitics, and we can put in our magnetic cores and really show you a very accurate effect of those more complex topologies as well. We have some application notes there as well. We send out to those who are interested.
Can you include layout parasitics in your simulations?
Yes, that's a very good question. So we have other tools that are not tied in PSpice in our Sigrity tool set that's post layout, where we can extract the layout parasitics and then get SPICE models for them And you can take those splice models and reapply them to your original schematic here and fully capture your layout parasitics. And then once you have those layout parasitics, you can then use some of our sensitivity and optimizer techniques and see how we can best handle those parasitics or what effect those parasitics have on our desired goals. That's a wonderful question. Thank you.
Is the PSpice capability included in OrCAD PCB editor, or is it an added cost feature?
So it depends on what package you purchase your PCB editor with, but it is its own standalone tool. So if you don't have it currently, you can buy the PSpice package on top of your PCB editor. But some packages out there include PSpice with your PCB editor purchase.
Can you do Bode plot in time domain simulation?
Can you do Bode plot in your time domain simulation? Yes, we do have some techniques and application notes that we can use to show you how to extract from your transient analysis, your frequency domain response. If I can pop open here. So I believe you can do some Fourier. If you guys go under your transient analysis tab, you can go into your output file options here and enable a Fourier transform and do some analysis there. We have some techniques for doing closed loop analysis on a transient analysis in PSpice, but I can share some application notes with you guys. But there are techniques to do that, yes.
Thank you, Roger. Looks like we have a few more questions still coming in, but unfortunately we are out of time for today. However, if anyone has questions that were not addressed during the webinar, you don't need to worry because we'll be following up with you on an individual basis. I will be closing the webinar now, and we will be sending everyone a recorded version of today's webinar with the slide deck within the next few days. Thank you for taking the time today to join us. Bye-bye.